Wiener filters are filters to reduce the influence of noise and distortion. So let's assume we have X of n, that is the original signal, and we have Y of n, which is our distorted signal. So here we have that Y of n is equal to X of n plus V of n, where V of n is assumed to be independent white noise. So Wiener filter will have this HW of n, will convolve HW of n with our distorted signal, and we'll get back our X of n, our original signal. So that's the idea what we want to achieve. So signal fidelity, so the reconstruction is close to the original. For instance, for denoising an image or audio signal, where the audio signal does not need to be deterministic. The goal here is an approximation of the original signal in the least mean square sense. So meaning we would like to minimize the mean quadratic error between the filtered and the original signal. So if we have a filter system with Wiener filter H of W, we have here X of n is equal to Y of n convolved with H of W. So this is our Wiener filter, this is our distorted signal, and this is what we want to get back as our original signal, or an approximation of the original signal, meaning that we filter our distorted signal Y with our still unknown filter HW of n. So the convolution of HW of n, so this is filter length L with Y of n, can be written as a matrix multiplication. So alternatively, we can run the sum in the other direction. So this is property of convolutions. So now let's define two vectors. The first vector of the past L samples of our noisy signal Y up to the present sample at time n. So both phases here are indicating that it's a vector. So this is, we are defining here our vector. So past L samples of our noisy signal up to Y of n. So the next vector contains the time reversed impulse response H of W. So this is, using those two vectors, we can rewrite our convolution equation, this one or this one, as a vector multiplication. So this X of n is equal to Y of n, this vector we constructed here, multiplied by this vector. This is the time reversed impulse response here. So observe that H of W has no time index because it already contains all the samples of the time reversed impulse response, and it's constant. So we can now also put the output X of n into a row vector. So we are transforming our signals into vectors. To obtain this column vector, we simply assemble all the row vectors of our noisy signal Y of n into a matrix. So we have this matrix with our Y of n, and with this matrix we obtain the result of our convolution at all time steps. So this matrix times H of W is equal to X of W. So we're implementing a convolution, but as matrices and vectors multiplication. So this is just another way of writing our convolution. So for example, if we have a filter of length 2, and this is H of W, so we have here our matrices of the distorted signal. We will multiply with this filter H of W, and we will get our X. Observe again that the vector H of W in this equation is the time reversed impulse response of our filter. This is now the matrix multiplication formulation of our convolution.